Okay, so this is a question. I've been meaning to do this question for a while, but I haven't had a chance to. So now is an excellent opportunity to do it. So this is a setup that looks like it's going to be, yeah. So the question says this: if the person remains at rest. So that's a phrasing that we use sometimes to indicate not only is the velocity of someone zero, but that their acceleration is also zero. And this is going to describe something that we are going to call static equilibrium. And we have a whole week set aside to do static equilibrium questions. This is, I guess, a little bit of an early taste. So we can treat this we've been handling all the Newton's law questions with standard strategy, which are the four steps of standard strategy are step number one, draw free body diagram. Step number two, define axis. Um, Usually, in paying attention to the acceleration, you try to make it so that x direction is parallel to the direction of acceleration. In situation like a static equilibrium, you get complete freedom in how to define axis, and you usually use that freedom to reduce the amount of complications that you might have. Three, break down forces into components. And finally, step number four, write down Newton's second law equations that acceleration comes from net force divided by mass of the object. So these are the four steps. Hopefully by now you are sick of it or you feel very comfortable with these four steps. So let me go through them. I'm going to start with the free body diagram. By the way, I've seen this in some of the other assignments where people are trying to draw a free body diagram on top of other diagrams. Don't do it. What I'm going to do now is what we recommend. You want the free body diagram to be really a diagram of forces. Anything else you indicate on it, you want to make sure you won't confuse them for force. So what I recommend is start with a dot, and on that dot, draw all the forces you have. And so so the dot is, I guess I'm drawing a free body diagram of this point on the rope. So there are a few forces acting on it. There's a force of this trapeze artist who's hanging from it, that's going to be equal to her weight, indicated as W on the other diagram. And there are two tension forces acting at that point. There's tension T1 going in this direction, and there's tension T2 going in this direction. And I'm looking at the numbers to be sure. Okay, so even though this looks like it might be 90 degrees, but I don't think looking at these numbers, they are actually 90 degrees. So make sure that you don't treat those two forces as being 90 degrees. So one of the decorations I might add to a free body diagram is to indicate the angles. So with T1, I'm given that this angle, let me label that theta 1, is 15 degrees. And I think in this diagram, I can say that this is that angle theta 1. You can kind of think of the parallel lines and some geometry theorems you might remember. Important thing is that this is theta 1 and not some other angle. T2, let me call this theta 2. Looks like that's already indicated where I would want it, so that's theta 2. So that's my step number 2. I drew all the forces. It feels to me like I've drawn all the forces. I didn't forget anything. And one of the things I look at to get a sense of if it feels like I've drawn all the forces is if it looks like I can satisfy my requirement regarding acceleration. With these three forces, I have a good sense that I can make these forces come out in such a way that they add up to zero. So I think I'm good. Okay, so we have to define axes, and in situation like this, I guess first, if it's possible, you might define your axis along one of the forces so that you have to break down fewer forces. In this setup, I don't feel like I can gain much by, by making my axis along T2 or T1. So let me just do the normal thing and let my axis be a straight axis, X and Y. That'll just reduce some of the headaches, and my gravity is already along the y direction, so I think it will be good. So with those axes, that was step number two. Now it's time to break force into components. So my gravity is already in the y direction entirely, so that's good. I don't have to break anything down there. So I need to indicate um, my T1 and T2 broken down into these two X and Y components. So for T1, my Y component looks like this, and my X component looks like this. And since I have the angle identified, let me just give these a label. So the Y component, it's the adjacent side, so it should be the hypotenuse times cosine theta 1. And my x component, it's the opposite side to the angle, so it should be t1 sine theta 1. Just remembering the mnemonic so ka. Uh, Sine of angle is opposite of hypotenuse, and solving it for the opposite side, I get this. Hopefully by now you've done this dozens of times, so all of this should feel mechanical. That is really our goal, for this to feel very repetitive, so that if someone woke you up in the middle of night and had you do this, then you would be able to do it in your sleep without making mistakes. So T2, I need to break that one too. I have my X component and my Y component. So X component, it's adjacent to the angle theta 2. So that's T2 cosine theta 2. My Y component, that's opposite to the angle. So that's T2 sine theta 2. And I want you to note how whether the component is Y or X doesn't necessarily match up with if you're using cosine or sine. So this is why I always recommend that you draw your triangles and work through the trig relationships. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. Go through that every single time because that's the only way to get it right every single time. Okay, we broke forces into components. And the fourth step is to write our Newton's second law equations. And these arrows serve as a reminder that it's a vector equation. So if you have two axis directions, two dimensions, x and y, then you are going to need a two equation for each object here. I have only one. So let me write down those equations. So my acceleration along the x direction, which is 0, because my whole acceleration is 0, that's equal to net force along the x direction. So I'm using this drawn diagram as my tool and just reading information off of this diagram. That was really the purpose of steps 1 through 3. So that as we do step number 4, all we have to do is read the information off of this diagram. I have my x component of t2 going in plus x direction, so t2 cosine theta 2. And I have x component of t1 going in the negative minus x direction, so minus t1 sine theta 1. And I think that's all the forces in the x direction. So all of that divided by mass of the point, which is infinitesimally small, but we don't want to say that's a zero, so this is going to be some non-zero value that we can frankly cancel out because the left hand side is zero. If we imagine doing this, if we imagine multiplying the whole thing through by n, left hand side won't change and right hand side won't have the mass. So that's what's in the back of my head, but for good problem solving hygiene habits, let me just write n so I don't forget it in future in places where they might matter. So acceleration along the y direction is also 0. So y direction, I have three forces, y component of t1, t2, and then weight. So let me write down y component of t1, t1 cosine theta 1 plus y component of t2, T2 sine theta 2, and then weight is going downward. Oh, and it looks like I'm given the mass of the performer. So let me write down my weight in terms of that mass. It should be m times g. So I'll write it down that way. So minus mass of the, oh, wait. let me write it this way, just so that I don't confuse people. So the M I'm going to write down, that's the mass of the performer. Let me write that with a capital M. The M that I wrote here, because I've been drawing free body diagram for this point, it's a mass of the infinitesimal portion of the rope. So let me be careful there. Um, so minus capital N times G. And here what I'm dividing by is the mass of the object that I've been drawing free body diagram for. Infinitesimal piece of rope. I think if you've been writing this for the trapeze artist, I think it'll result in a harmless error, as in you might have mixed up these two and still overall gotten a correct answer, which is fine. But I, again, want to demonstrate proper problem-solving hygiene, good problem-solving techniques, habits, so that for the harder questions, these things don't trip you up. So, right. So this is the step where standard strategy leaves me with. It's given me a system of equations, equation one and equation two. And my hope is that I have only two unknowns that I need to solve for. Let's watch here. So we are being asked for T1 and T2. I have T1 and T2, two unknowns. Do I know everything else? It looks like I know everything else. I know what my mass of the performer is. And even though I don't know the mass of that infinitesimal portion of the rope, if you imagine doing this that I sketched earlier, then that small m cancels out. So that's not an unknown that you have to know anyway. So I got two equations, two unknowns, so I should be able to solve for it. Now, um, in a lot of the questions from this point on, I would have done this by hand, and I can also still do by hand. But since you have so many examples of these questions where I'm solving the question by hand, let me show you an example of using computer algebra system. So here, I'm just gonna say use computer algebra system like SageMath. And two equations, it's probably not complicated enough where, uh, like using, it's like it's overkill. I don't really have to use computer algebra system to do this question, but let me just show it as a demo, just so that people can see that if you feel not quite fully comfortable with algebra, you don't have to let that be something that holds you back. There's a tool like a calculator that lets you work through algebra like using calculator. This is calculator for symbolic algebra. So when you're using SageMath, so the main thing that main function that you have to know, you might use a documentation or some way to look it up, help. The function that you need to know how to use is a function called solve. It's a function that will let you solve for a system of equations. And it's particularly powerful in dealing with the system of linear equations like what we have. So this documentation gives you examples and whatnot. So let me follow some of those examples. So I need to define the variables I will be using. T1, T2, theta 1, theta 2, I don't need the small mass m. I'm gonna write down the version of equations where I've canceled them out. I do need the big mass m, and I do need the g. Okay, and in the documentation they have you assign these into those. I found that you don't need to. Just this declaration defines those variables, and they are ready for use. Let me write down my first equation that's based on the x direction, equation 1. That's going to be, so this is an assignment symbol, and the equation will be 0 is equal to, this is the equal to symbol, t2 times cosine of theta 2. SageMath knows these special functions, and um, yeah, and there's documentation that you can look up to figure out which functions it already knows and whatnot. minus t1 times the sine of theta 1. Okay. And I'm going to write down a version of the equation where I've already multiplied it through by m, so I'm not going to write m at all. So when I do this, okay, it doesn't complain, so I'm going to assume it's right. Equation 2 is equal to 0, or equation 2 should be assigned as 0, being equal to t1 times cosine of theta 1 plus t2 times sine of theta 2 minus m capital M times g. Okay, and I entered it. By the way, so I use shortcuts when I enter this. So here I use the shortcut for I think it's under cell shift to enter, run cells and select below. So if you are using SageMath, like this exact setup that I have, and like when you press enter, it does this instead of what it did for me. Then it's because I'm using shortcuts. Let me know if any of that is confusing you. Um, so let's just verify that we have those two equations defined correctly. So I'm just doing this to print them. Yeah, those are my two equations. They look right. I have that minus sign there. Okay. So with the solve, this is, you can see the syntax in the example here. It's a solve and then the system of equations and then the variables to solve for. And yeah. And when you do that, SageMath will assume that all the other variables are known quantities. So I'm gonna have this system of equations, and then I'm gonna solve for T1 and T2. And it'll assume theta 1, theta 2, M, and G, all those are known. So it'll do that in a bit. There it is. That's my solution. Let me put that into a variable called source. And I can see that it's giving me a nested array. And that's mainly so that sometimes there's more than one solution. So that's why it's doing that nested thing. I'm just going to get the first element. So solutions is previous output, or yeah, let me just use that. And then the first element, and then I think then it's just an array of two elements here. So let's see. Yeah, good. So if I look at the first element of this array, that's my solution for T1. So the question, so let me do it this way. I think I can just plug in the numbers using SageMath. I have all the numbers here. I can just plug in the numbers that way. So solves. I'm going to use something called the substitution syntax. So we are substituting T1, not T1, M is equal to uh, 56 kilograms and G is equal to 9.8 meter per second squared. I'm just going to make sure I plug everything in basic SI units so that my answer will be in basic SI units. I need theta 1. Now, SageMath only understands radians, not degrees. So I need to enter theta 1 as 15 degrees and then convert it to radians, pi over 180. And then and let me actually make sure this is in a decimal approximation. Theta 2 is 10 degrees, so 10 times pi over 180, so that it'll be in radians when it calculate. Okay, I think that's all the numbers I need. Let's see if it gives me, yeah, a numerical value, 542.5. And let me do the same thing for, let me copy and paste this. So this is not time, it's the second element, which is T2. And I already have all the parameters values here, so just shift enter. And that's my value of tension 2. 142.6. So let's try that and see if see if it works. 542.5 and 142.6, and it agrees on 1% tolerance. So I didn't actually need that fourth digit. Three significant figures should be enough. So yeah, that's the correct answer. So yeah, as I was saying at the beginning, it is a substantial question. You do have to go through this standard strategy, and it does take some time. So make sure that you spend the necessary time. And in terms of doing the algebra, if solving for system of equations trips you up, feel free to use SageMath. Use of SageMath, like use of calculator, is allowed in every single circumstance.